let z1, z2 all the way until zk be independent random variables and following a standard normal distribution. Show that z1 squared plus z2 squared all the way until zk squared follow a chi-squared distribution with the degrees of freedom of k. So to do this, we have to use the MGF method. So one of the properties of a moment generating function, let's call it property 1, is that if the moment generating functions of two random variables are the same, then A and B follow the same distribution. Well, this property tells us that to show that if z1 squared plus z2 squared all the way until zk squared follow a chi-squared distribution, then we just have to show that the MGF of z1 squared plus z2 squared, plus all the way until zk squared is equal to the MGF of a random variable following a chi-squared distribution, then we have z1 squared plus all the way to zk squared follow a chi-squared distribution with the degrees of freedom of k. Well, therefore, we need to find this part and this part. Okay, first, let's get the easier part that we kind of already know. We know that the moment generating function of a chi-squared distribution is 1 minus 2s to the power of negative k over 2. This is something that most textbooks already have, or you can check out a future video of me proving this. So now we just have to find the second part, mz1 squared plus z2 squared all the way to zk squared. So to find the second part, we have to use another property of MGF. Is if x1, xn are independent random variables, then the MGF of them added up together equals the MGF of a single one of them multiplied by the other one of them, etc. Again, I could also prove that in a later video. Then, once we know this property, then it would be easy to find the moment generating function of z1 squared added up all the way to zk squared, because that would just be the moment generating function of z1 squared multiplied by moment generating function of z2 squared, etc. Because from the prompt, we already know that z1, z2, all the way to zk are independent random variables. And since they are independent, then their squared values must also be independent. And since we know that all of them follow the same distribution, aka a standard normal distribution, so we know from here, then we know that their single moment generating functions must be the same, aka this is the same as this is the same as this. So if they're the same and they're like multiplied together, it basically means that so if this, for instance, the same thing, like a multiplied by a is multiplied like k times, then this means that it's just the exponent of the a to the exponent of k. So once we know this, we know that this is basically just, for instance, mz1 squared, the moment generating function of mz1 squared to the power of k, because they're the single, like mz1 squared equals mz2 squared equals the moment generating function of zk squared. So if them multiplied by k times is basically the moment generating function of one of them to the power to the exponent of k. Okay, so now once we have established this, we just have to find the MGF of z1 squared. Oh, sorry. And the definition of MGF, if you forgot, is, okay, let's put it here. So the definition of MGF of, let's say, x is the expectation of e to the power of sx. So this, the MGF of z1 squared s would be the expectation of e to the power of sz1 squared. And now let's talk about properties of expectation. Let's use another color. So if you forgot, the meaning of expectation for a continuous variable is you take the integral from negative infinity to infinity, or like the range of x times the PDF of x dx. And the expectation of a function of x is basically the same thing, but you replace x with g of x. So basically in this case, this e to the power of sz1 squared, this is basically just a function of z. So we could use this property to show, okay, let's use this color. We use this property to show that the expectation of e to the sz1 squared is basically the integral from negative infinity to infinity of e to the sz1 squared. Actually, why am I using this color? Okay, one sec. The integral of negative infinity to infinity of e to the sz1 squared power times the PDF of z1. It doesn't really matter, but the PDF of z1, guess what, is, since z1 follow a normal distribution, then the PDF of z1, if you forgot, is this PDF of z1 equals 1 over root 2 pi e to the negative z1 squared over 2. So this is the PDF of a standard normal distribution, distributed variable. And again, you can find this in any textbooks. So now once you get fz1 squared is z1, you can plug that in. Times 1 over 2 pi, root 2 pi, sorry, times e to the negative z1 squared over 2 dz. Z1. Okay, let's just say Z1 is Z because or else I'll have too many subscripts, but basically this is a pretty hard integral to solve. So let's combine the e terms first. Let's combine these two terms. So that's e to the power of z1 squared minus z1 squared over 2 dz. Okay, this is still like really hard to solve, so let's kind of simplify this part. Actually, let's simplify it over here just so that we don't disturb all the other stuff going on. Okay, I'll copy it down again. So minus 1 squared over 2. Okay, so this is basically s1 squared minus z1 squared, actually 2s1 squared minus z1 squared over 2. So this equals to 2s minus 1. Actually, since we do kind of want to keep the negative, you'll see why. It's kind of 1 minus 2, negative 1 minus 2s times minus z1 squared over 2. And then I'm gonna do something really weird. I'm gonna put this little function down here. And to do that, you just take the power of negative 1. You'll see why I'm doing this, but it's very useful. Okay. Now we put this whole monstrosity back. So we put this whole monstrosity back to where it belongs. Here. Let's put it here. Okay. So equals e to the power of negative z1 squared over 2 1 minus 2s negative 1. And then dz. Don't forget the dz. That's important. Okay, so now it didn't get any better, didn't it? But what we have here is very promising. Why? Because recall that the PDF of something following a normal distribution equals, oh wait, no, there's no integral for PDFs, equals sorry, 1 over excuse me, 1 over root 2 pi sigma times e to the power of negative x minus mu squared over 2 sigma squared. Okay, so this is very promising because you have, okay, here you have a 2, and you also have a 2 here. You have something squared, and you have 1 over root 2 pi. And yeah, so the structure looks really similar. In fact, the structure looks like if, for instance, mu is 0, so if this is 0, and then if sigma squared is 1 minus 2s to the power of negative 1, then it looks very similar to the PDF of when mu is 0 and sigma squared is 1 minus 2s to the power of negative 1. So now we're missing a thing over here, right? There's nothing over here. It's missing something. It's missing a sigma. And we know that sigma, wrong color. We know that sigma is 1 minus 2s to the negative half. So it's basically like root of sigma squared. So now we could, to put something in that little spot, we just multiply by like the numerator and denominator by the same thing. So it's basically 1 minus 2s to the negative half over root 2 pi 1 minus 2s to the negative 5. So this is basically like multiplying by 1, so it doesn't really affect anything. And then we just copy down the rest, yada yada. And now we get something very similar to the structure of a PDF of a normal distribution where the mu is 0 and the sigma squared is 1 minus 2s to the power of negative 1. But I guess the only thing that differs is we have to take this value out, which is possible since it's like not a function of s. It's a function of we're taking the integral of dz with respect to dz, so we could easily take this out. It's basically just a constant in this case. So this is 1 minus 2s to the negative half multiplied by negative infinity to the infinity integral 1 over, I'm just copying everything down, e to the negative 0 squared over 2, Okay, so now we have this monstrosity. So this, actually let's not include the dz in here. We have this monstrosity is basically the PDF of a normal distribution with a mean of 0 and a variance of 1 minus 2s to the power of negative 1. Okay. And we know like the PDF of an integral, like if we take the integral of the range of all the values and of a PDF, then that's 1. That's the definition of a PDF. So if we take the integral from negative infinity to infinity of a PDF, then that would be 1. Okay. So since we've established that this would just be 1 minus 2s to the negative half times 1, which is, just this. And then, so we now know that mz1 squared, the moment generating function of z1 squared is 1 minus 2s to the power of negative half. Phew, that was a mouthful. That was a lot to digest. But let's go back to earlier. We established that. Okay, I'm gonna copy this. Oh. Okay. I'm gonna copy this thing. We've established that the moment generating function of z1 squared plus z2 squared all the way until zk squared is basically just the moment generating function of z1 squared to the power of k. So this is basically 1 minus 2s to the power of negative half to the power of k, which is basically 1 minus 2s to the power of negative half, negative k over 2. K over 2. Okay, so we get this thing, which is lovely because if we go back here, let's found that earlier we've established that if the moment generating function of z1 squared plus z2 squared plus zk squared equals to the moment generating function of a chi-squared distribution, and z1 squared plus z2 squared plus all the way into zk squared follows a chi-squared distribution. And as we see over here, they're in fact equal. This is equal to this, which means that per property 1 z1 squared plus all the way until zk squared follow a chi-squared distribution. And voila! That's how we solve the problem using MGF method. I'll probably download this and put it on a Google Drive for you to view. But yeah, finally we're done.